Hi, my name is Stephanie Quigley, and this is my Challenge Assessment 6 Control System Design Project. The objectives for this project is to design an active or a passive compensator for our lane changer. And we want to improve our transient response peak time about 75% and maintain or decrease the overshoot in the compensated system while also maintaining a zero steady state error. So the first step is choosing what kind of compensator we want to use. So for a PI and a lag, we can see that those are used to improve our steady state error. Now, we're not looking to improve it, we just want to maintain what we have, so we can go ahead and cross off these. Now, the next one, a PD and a lead compensator are used to improve transient response, and we do want to improve our settling time, so we'll come back to that. Our third one for a PID and a lag lead is to improve our steady state error and transient response. And again, since we don't want to improve our steady state error, we don't need to use these. So now looking back at a PD and a lead, the difference is either adding a 0 or adding a pole and a 0. And on the bottom, we can see that adding poles actually slows down the settling time, and adding zeros speeds up the settling time. So we want to avoid adding poles. So that's why we do not want to use a lead. So we actually want to use a PD controller for this design. Next, let's take a look at the block diagrams. We have our variables defined over here. And over in our block diagram, we want to have our output be the position of our system. So we will move this block over, and that will create an S squared block down here. And once that all simplifies out, we have this final block diagram here. And we will also combine these blocks again to create a unity feedback, and the reason we want to do this is so that we can find our steady state error. So in unity feedback, we can find what type system we have, and we can see that we have a type 1, and when solved out, we can see that we have a steady state error of 0. So back to our objectives, we want to make sure that we maintain that steady state error as 0. Now let's evaluate our uncompensated system. So we have our open loop transfer function, and we're going to use that to plot the root locus. And as you can see, we have no zeros. We have 4 poles, and those poles are located at 0, -1, and there are also 2 at -10. We can also find some characteristics, include WD, sigma, and zeta, which will be used to help us solve for our compensated system. Another good thing to do is check for our second order approximation. So at gain 2, we're going to check to see where sigma is at. So here we have a sigma at -10, and the other one at -0.454. And that is 5 sigma away from each other, which is good. That means we have our second order approximation. Now we are going to look at the closed loop step function when our gain is equal to 2. And this is what the step response looks like. And we can see that we have a settling time of about 9.4 seconds, and our overshoot is 3.7. And this is what we will look at to try to improve when we look at doing a PD compensator. Let's find this closed loop pole location at 75% of our settling time. So we're going to multiply our settling time that we had before by 75%. So we're looking for a time of about 5.4 seconds. And then using this, we can solve for our WD and our alpha, which will eventually lead to our sigma compensated. And so now our new pole location we want is at -0.6 plus or minus 0.5. So now we're going to use the compensator angle contribution to solve for where our 0 will be located. And so we have a pole, so we want our pole at about 0.6 like we just found, so that's going to be about here. And we're going to use this compensator angle contribution to find our angles. So so now we have let me change colors here, an angle theta 1 here, an angle theta 2 here, and then we also have 2 angles here for our 2 poles at -10. So solving for these values, we get a compensated angle of 18.9, And then we'll also use that angle to help solve for our 0. And we'll find that we want to put a 0 at 2.29. Let's evaluate this new 0 now. So we're going to plot our root locus for our open transfer function. And this is our result. We also now want to find the gain at the location that we had found before. So when we go to that pole location that we had found, we see that the gain that we want is 1.44. Now again, let's check to make sure our second order approximation holds. We have a sigma at 1.43. Oh, I'm sorry, that's not right. We have our pole at negative 11.5 and our other pole at negative 0.603, which is 5 sigma away, so we are good to go there. So now let's see what our PD controller will look like, because we found our gain at 1.44. Now let's take a look at what adding this new PD controller does to our step response. So we can see that it has improved the settling time from 9.4 seconds to 6.66. We also decreased our overshoot from 3.7 to 3.6%. And lastly, our peak time, it was 7.1 seconds, and we were able to reduce it to 4.96 seconds. And you can also see the difference in the plotted step responses here. So in summary, we designed an active compensator and used a PD controller design. We improved the transient response peak time to 75%. Our original was at a peak time of 7.1 seconds, that should say TP, and our PD controller is now at 4.96 seconds. We also decreased our overshoot from 3.73 to 3.61%, and we also maintained our 0 steady state error. And that is all I have. Thank you.